Good afternoon, ladies and gentlemen, and welcome to our online technology meeting on Mid-Infrared Alliance Present and Future. I start sharing the screen, so we will recap the situation. So, for most of you already know EPIC, the European Industry Photonic Consortium. For those who doesn't yet know, EPIC is the largest no-profit industry association with more than 750 members working in the photonics field, from laser to microoptics, from display to atomic and quantum technologies. We foster a vibrant photonic ecosystem by maintaining a strong network and acting as a catalyst and a facilitator for the technology and the commercial advancement of our members, of the markets, and so on. How we do it? We do it with the support of this great team made of 14 persons that are engaged to easy the market access for all the members, that are really working on proactive networking. They are developing mentorship program. Also, there is a specific website dedicated to the job in photonics, as well, last but not least, developing and supporting the investment in this industry. Among all these great colleagues, I would like to introduce my colleague Francesca, the program manager who helped in the preparation of this meeting and who will drive me in the discussion of this afternoon.
Thanks a lot, Antonio. So welcome everybody also from my side. I guess, yeah, just a word. It's me as well here with you. Black shirt, both of us. So Antonio, thank you for the introduction. I give it back to you.
Okay, thank you so much, Francesca, for your energy. And really, we are speaking about thanking. So it's important also to thank the members, our friends that decided to support this meeting of today. We can start around Europe as usual. We can start from the sunny Barcelona with IMASENIC, who is developing a custom image sensor and readout integrated circuit. Under a recently awarded EU grant, is developing also a new type of solid-state imagers for simultaneous detection of visible and medium infrared. Then, going north, we meet SUS MicroOptics, which manufacture high-quality refractive and diffractive microoptics for application in automotive, photolithography, fiber optics, silicon photonics, and many other applications. Then, entering into Germany, we have Excelitas, that is really enabling the future for light, with their unique ability to deliver photonics solution tailored to your specific requirements. We remain in Germany, and we can drive to Würzburg to meet nanoplus, with their laser that they cover a huge range of wavelengths from 700 nanometer till 14 micron. And finally, we reach Berlin. We reach Art Photonics, one of the few worldwide leaders in the MidIR fiber optics from 2 to 16 micron, polycrystalline fiber, hollow waveguides, and assembly and assemblies for this fiber. But then we can go also a special thank to our panelists. Today we have really a great partners to lead this discussion. We will discuss today about the future, the current and the future perspective of the MidIR technologies and the MidIR Alliance. During the EU-funded project named MIRFAB, has been created a very active community that, after the successful conclusion of the project, in the summer 2021, decided to proceed and to found the MidIR Alliance as a tool to keep together and make wider such ecosystem. Today, we will discuss, following the fil rouge of the two classical EPIC questions: what can you do for the others, and what can do the others for you? And this time, I also had a third one: what can do together to reach the end users and to match better their needs. So I really welcome Professor Aamir Farooq from King Abdullah University, Mathieu Carras from mirSense, Adam Piotrowski from Vigo System, Johannes Koeth from nanoplus, Samuel Poulain from Verre Fluoré, Antoine Muller from Alpes Laser, and Viacheslav Artyushenko from Photonics, and all the participants. Francesca, which are the participants today?
Thank you, Antonio. Then we can exactly, this slide shows exactly the other people that the panelists are important. But as we heard today, we have 3 epic questions. So definitely we cannot answer these questions without the contribution of also all of you here in the room together with the panelists. As usual, it's important to talk about the end users of the technology because they have to tell us how we can support them. And so few of them are in the room, and also the system integrators. In this case, we are talking about middle and low-level technology that can be really much be integrated in cameras or the other system for example, environmental sensing, or anyway for services, even for gas sensing. So they are also here to tell their opinion and to tell how to the components provider how to work together and how to bring more MidIR into the market. But nevertheless, I mean, all the others is not that they are less important. Everybody has his own contribution, providing lasers, maybe MidIR, but not only. Everybody is here also listening from other wavelengths, maybe not known for MidIR, but I bet they want to see and hear what is the future of MidIR. And all of these, of course, materials in thin film, you see a lot of people because it's a challenging wavelength range. So they have also to hear and to learn how is important for them to push for MidIR. And then, of course, spectrometers, specialty fibers. We heard already, we will talk a lot about this, about the lasers, a lot of quantum cascade lasers. So for sure, this will be the main topics, but all of you here in the room, including the R&D, please feel free always to interact, ask questions, and tell what is your feeling about how to bring all this strong community together and to be successful. But now, maybe we go back to the agenda, Antonio, and we start because it's not important to talk too much in introduction. Let's give the floor to our panelists, and it's a great pleasure to welcome Aamir, and it's from Abdullah University and from King Abdullah University, and as a basic and important end user of the MidIR technology, he will tell us a bit more what is his experience and what is maybe his needs for the future. Thank you, Aamir, for being here, and please the attention and the floor is of the attention of everyone, and the floor goes to you.
Okay, thank you, Francesca, for the kind introduction. Thank you to Antonio and also other members of the APIC team for inviting me and giving me this opportunity to speak with everyone. Actually, it is an unusual setting for me personally to be in the middle of so many great companies, people that I've seen, some of the names definitely from the panelists, but this is the first time maybe seeing you virtually in person. I'm here really more to learn from you guys than to really tell. I'm sure there are many things that you have developed over recently that I'm probably not aware of, and especially the pandemic has thrown a wrench into our plans of meeting and attending conferences. So anyways, I hope this will be a beneficial interaction for me and for you as well. Okay, so again, as introduced, I'm at KAUST, King Abdullah University of Science and Technology in Saudi Arabia. It's a research-focused university with master's and PhD programs only. My lab is called Chemical Kinetics and Laser Sensors Lab. I've been here in KAUST for about more than 10 years, and before that, I got my PhD in States at Stanford University. So just there are two parts of my talk. First, I'll tell you a bit on what we do and very quickly a couple of examples, and then I'll tell you what are some of the needs. And I know I have to do all of that in 6 minutes, which is much difficult than to give a 60-minute talk. So the focus of my lab is on three aspects: precision spectroscopy, laser-based sensors, and then fuel kinetics. So we look at rotational and vibrational spectroscopy, and particularly we focus at high temperatures and high pressures, and we look at some advanced spectroscopic models to understand the spectral changes. Then we try to develop compact portable laser-based sensors using various techniques, sometimes just absorption, sometimes wavelength modulation, sometimes frequency comps as well, sometimes short pulse, cavity enhancement, and so forth. And the idea is to apply this to chemical kinetics, environment monitoring, and some biomedical applications. And in the area of fuel kinetics, we are looking at low carbon fuels, zero carbon fuels, efficiency enhancement, emission reduction. And this is where the laser sensors are really helpful to us for understanding the physics and chemistry of the processes that we want to understand and optimize with the help of sensing. As an axis of wavelength, in my lab, we've been working over the years all the way from the ultraviolet region to near IR, but a lot of work has been done in the mid-IR. So these are just some examples of works we have done at various wavelengths using different kind of lasers, measuring different species, various applications ranging from, again, chemistry to environment monitoring and so forth. So I won't go obviously the detail of this. This is just to give you a snapshot that over the years at KAUST, we have worked over these sort of the entire range of this mid-infrared wavelength. And lately we've been focused more and more at longer wavelengths. Just as an example of work we did for a local industry for Saudi Aramco and their environmental protection department, they came to us, they wanted a very sensitive sensor for benzene emissions. So we utilized an interband cascade laser near 3.3 micron. We used cavity enhancement with high reflectivity mirrors. And basically we delivered them a sensor which can do measurements of benzene, where benzene was the main aromatic that they were trying to look for with a detection limit of 2 parts per billion. But then next they made it more challenging. Sorry, before that, the stage where we are with them together is now that lab-based prototype that you see here. They want to convert it to something much more portable. How can we put it on a drone and fly it around their gas fields or take it to some other remote locations? And this is where I hope I can get some ideas from all of you on how we can package that lab-based sensor and put it in something small that can be taken over there. So this is the vision where we want to go. But then they came to us with another problem. They said now they're interested in BTEX, which is a family of aromatics, and they want to do selective measurements of benzene, toluene, ethylbenzene, and the 3 isomers of xylene. And their spectra is somewhat different in this CH stretch region. But if I zoom into one laser, one ICL that I will use, then it's a bunch of flat lines, their spectra. And it just becomes very, very difficult to isolate them and selectively tell each species. And this is where we have done some work on using machine learning algorithms and some other techniques to isolate these species. And that's an ongoing work that I will not go into the details. So there's the CH stretch, which is the sort of relatively low wavelength mid-IR. And there's the CH bend region, which is the long wavelength mid-IR. And you see the spectra are more resolved, more separated in the CH bend region. But the problem that we have there until very recently is that there was no commercial laser availability in that very long wavelength region, especially near 15 micron. So we worked collaborated with a group in Politecnico Milano, and we developed our own DFG-based laser, combining an ECQCL and sometimes a DFB-QCL with a CO2 gas laser through an orientation pattern gallium arsenide crystal. And then we got the long wavelength laser. And this is a picture of the laser system that we developed. But of course, this is not field deployable. I can't take it to a petroleum field and do measurements with it. And this is where we've been collaborating with mirSense and have obtained a laser from them to do such measurements with that. So finally, I'll just say a few things on what does the industry need. From my conversations with the local industry in Saudi Arabia, the petrochemical industry primarily, they want to sense everything, everywhere, all the time. This is a phrase I like from my friend Greg Rieker as well. These should be field deployable sensors, portable, lightweight, small, low power. That's what portability means to them. Rugged, you just install it there, works all the time, remains stable. Highly sensitive to what you want to measure, selective as well, accurate, low cost, very key here, low cost. They want it as cheap as possible. Calibration free, so there shouldn't be any need of someone to go turn the knobs. Super fast, do it on seconds, maybe faster, and then can do multi-parameters or multi-species. So some of the recent needs from the local industry, I've given a list here. I won't go into the details of it, but some of this is like looking at complete profiling of natural gas. Others, their needs are more on liquid-based sensing, water cat sensing, oil and water sensing, emission detection of various substances, rheology. Optical rheology is also important for them for some oil-based applications, and then online characterization of fuel and crude. And the conditions are super harsh here. Ambient temperatures can vary a lot, and then the process conditions could be hundreds of atmosphere and hundreds and thousands of Kelvin. So why MidIR then? You guys all know this. I don't need to say it. You go to longer wavelengths, you have more absorbance, more selectivity, so and more sensitivity. But why not MidIR? Is these things are not easy right now for MidIR. Field deployment, portability, ruggedness, low cost are challenging to make it happen with MidIR. So what do we need, at least from my side? And again, I'm here to learn from you. We need even better lasers, widely tunable, fiber coupled, low power consumption, room temperature operation. No need for me to bring in a chiller with the laser. Low cost, better detectors. Yes, the detectors are good, but they are not as good as in the near IR. And I know there are some material limitations, but what can we do to overpass those? Higher sensitivity, again, fiber coupling if possible. Fast time response, larger area. Can we have balanced detection as easy as it is in the near IR? And then, of course, there's more that can be done on the optical component side as well, on fibers, athlons, highly reflective mirrors. We sometimes run into a lot of difficulty in getting cavity mirrors in the MidIR, and sometimes their costs are just too much. And compact laser controllers so that we can package all of it together. And with that, I will end. And sorry for going maybe 1 minute over my allocated time. This is the shortest talk that I've ever given. So
Aamir,
it's a record.
Aamir, don't worry. Aamir, it's fantastic. And I thank you. We have to thank you because in these dense slides, you really put the question on the table, the topic. So here we have a lot of requests or needs from Aamir. Who would like to comment? Here I see, yeah, this is really the point of view of the end user or of the system integrator, meaning a system integrator, somebody who has to develop a system and supply to the end user. So he asked for compact devices, fiber coupled laser sources and detectors, easy to deployable everywhere. So I see Peter from Enlair and also Slava from Photonics. Maybe first Peter, please go ahead with your question.
Yes, hello, I'm Peter Totrup. I'm the CEO of a company called NLIR. We make infrared spectrometers. So many of the things you're looking for, we already have. So some of the features we don't, but we are on our way there. So I can share a slide very fast.
Yeah, sure, please.
Let me stop sharing them.
Can you see my slide or?
Yes.
So we make these spectrometers and detectors in the mid-infrared, and we can do kilohertz spectroscopy if needed, and also very, very sensitive and broadband high-speed detection. So I think we should talk after the meeting.
Definitely, it's good to know. Thank you.
Sure. Thank you so much, Peter. And that's a first answer. Good. So I see Slava that raised the hands, and then also Johannes from nanoplus. Slava, go ahead.
Yeah,
please.
Very shortly, I will have a short presentation at the end of the session, but what I like in your presentation, Aamir, you already mentioned that you need, let's say, components which are fiber optic pigtailed, because what is the most essential for all of us? Because most of us are manufacturers of components, and few of us are doing, let's say, integration of components.
Mm-hmm.
But the main driving force for any business, and especially for mid-infrared, is, of course, to understand well what for. And if you really can help us in this respect, because what I should comment, request for the broad range spectroscopy in many applications is excessive. It's needed only for the, let's say, pilot or research phase. Later on, when you use a process and you should, I don't know, control ethylene production, and you need only 3-4 trace gases to control, then you need only few selective wavelengths, information rich, okay, maybe 1 or 2 for reference, and then it means demand exists for the customized sensors. That's why here I would like really to have our, how to say, prolongation of discussions just to understand what for. Because then either it will be with nanoplus, with Vigo, with Peter, you know, we can always find, you know, what is the best components to be assembled in puzzle, which will meet your demand, because broadband spectrometry is always not a cheap toy. Yeah. And that's why you really must know what you need. If you need, let's say, only 3 colors when you're crossing the light on the street, in many cases, it's enough. Yeah. So green, yellow, red, you know, if you can define it in your application, then we can develop in MidIR Alliance specific sensors for your applications. That's it.
That's an excellent comment, and I agree with you. I'll just make a short reply to that. Is what I meant, maybe wide tunability, because it can mean many things, is not something that covers 3 to 15 micron, for example, right? What I mean is maybe more of the order of, let's say, 60 to 100 wave numbers of that order, right? For example, what I showed for BTEC spectra to you, right? When we were looking at a 100 wave number window, we could see their structure and we could resolve them better. But when we go to the typical scanning range of a DFB laser, which is of the order of a few wave numbers or 10 wave numbers in most cases, then for these large molecules, the spectra become just flat, right? So I think that's sort of the range that I mean is, you know, if tens of wave numbers can be accessed with a single laser, that's much easier than me having to, you know, put together 3 or 4 lasers, which is sort of what we are designing right now, right? Is having to couple 4 lasers, make them collinear and all of that. So that's sort of my response, but I agree with you.
Very important from our role, you know, because a lot of applications can be realized with detectors without any fiber optics. And we are not trying to, let's say, to push, you know, to promote fiber optics when it's not needed. But I understood, at least to our knowledge, from petrochemical, chemical industry, even from food industry, it's not always easy to take a sample and to bring, you know, for measurements. That's why if you should go with fiber probe in the pipe or reactor, and it will be high temperature, aggressive gases, you know, liquids, you know, vibrations, what else, you know, electromagnetic fields. Everything is possible, and we are doing fiber optic pigtailing for any source of infrared light and any detector. That's why we really cover even the range up to, let's say, UV. And today we are all focused on mid-infrared, but I should say we should not build up kind of Berlin Wall around MidIR Alliance, because there are some applications when you should really use so-called multispectral approach. It can be visible and mid-infrared together. So we should marriage the whole electromagnetic range. And again, fiber optics is available from UV up to 16 microns, not a problem.
Thank you.
Sure. Perfect. I remember that Johannes raised the hand.
I have a question.
So many... yeah, Johannes.
So for this BTEX application, you only used 1 nanometer of tuning range. Why did you do so? Because normally I can share a slide. Typically you have a larger area. Here's an example from one of our lasers at 5.2, where you can tune over tens of nanometers. So it's a little bit depending on I think the laser. You need better lasers, and they are available from us. So just have a look into our datasheets, perhaps.
Okay, we'll do that. That laser in particular is also from you, the ICL that we use.
Okay, but then we should talk again, because perhaps you can tune in a little bit further.
Yeah, I think, and I know that we can, but a little bit further will not help that much, because you need actually tens of wave numbers to start seeing some structure. Okay. And I guess we were trying to not change the temperature of the substrate, but rather just do more tuning with the current. That was the idea. But yeah, I understand that if you change the substrate temperature, that could give us more tuning.
Okay.
But thank you.
Thank you.
Antonio, you're muted, so I give the floor to Scott from Sivers Photonics, because I guess that is what he was saying, Antonio.
Thank you so much. No, because I was looking for the icon. This is so many people today that is I'm a little lost. But
no,
thank you
Scott,
so much, Francesca.
Yeah, no, your problem, Scott. Yeah, now you're not muted anymore. Please, you can ask your question.
Hi there, hi everyone. Sorry, that was very bad timing. My internet connection just cut out there when I was about to get asked. Hello to everyone. So my name's Scott and I work for Sivers Photonics. Aamir, I've sent you just a connection request on LinkedIn just to reach out. Sivers, we manufacture IMP-based light sources, including lasers and QCLs. So I just wanted to make you aware, just in case if you have any requirements for these, and also for anyone else, if you're looking for any infrared light sources, please give me a wee message and get in touch. That was all.
Yeah, thank you.
Cheers, guys. Thank you.
Thanks a lot, Scott. Thanks a lot. So the connection will be done now or after the meeting. So that's very good. Now I make a bit the ambassador of YouTube. So just to remind you, it's not only us here in Zoom. There is a lot of people also on YouTube. And I have a question today from Aamir Gadimi that is not in the room. It's weird. Aamir, what are you doing out in YouTube? From CSCM is another Aamir with only one A. And he's asking the question came before you commented on the tunability range, but he asked explicitly, please, can you say it in nanometers? So let's maybe repeat it again. So you said at the beginning, you don't need all the lasers, of course, to be tunable 3 to 15 micrometers, but you were saying sometimes also a 10 to 20 wave numbers, or anyway, what the DFB lasers can do could be enough. Can you maybe specify based on this so that the other Aamir has also a clear mind on what he can provide from CSCM side? Thank you, Aamir.
Yeah. Thank you for the question. Yeah. I mean, I think, again, there's no one answer to that question on how much tuning you need. It depends on the problem, right? So I was just giving that example of maybe you need tens of wave numbers, keeping it general, because for that particular BTEX problem, we needed a larger tunability to reach there. But for another problem we are looking at right now, for example, to do C1 to C5 molecular sensing. So there, we are probably going to need a different amount of tuning. So again, it depends on each, but roughly speaking, I said tens of wave numbers could get you to a situation where you would probably not need to add too many lasers together to do what you want to do.
Okay, thank you so much. And I think that we started very strongly, and we go on. I saw that you used a laser from mirSense, and the next speaker is Mathieu from mirSense. So now we will learn a little more about the laser that you used, and also we understand why you had to modify, or what has to modify, Mathieu. Mathieu, the floor is yours. You are muted. Still muted?
Not muted, yeah?
Ready.
Hello.
Go.
Thank you, Antonio, for the opportunity to talk today, and thank you, Aamir, for your talk. Yes, indeed, I will explain to you what mirSense is doing for gas sensing, especially using quantum cascade lasers, and in particular what we have done for Aamir in order for him to have I would say a simplest version of the setup using directly a semiconductor laser instead of something that is maybe a little bit more complex to obtain the same wavelengths. So first of all, so mirSense is about 25 people dedicated to innovation. So numerous key patents in QC and photoacoustics. And we basically have two manufacturing facilities in Paris and Montpellier, and for semiconductor chip manufacturing. And in Grenoble, we do integration and gas sensor developments. And I want to stress out that compared to what was said today, indeed, integration and going to the sensor is certainly a way to try to solve some of the issue of using mid-infrared in general, because it's not only having the component that is complicated, it's how to integrate it and get something that can be used. And we've seen in the different aspects that were raised by Aamir that compactness, cost, robustness, a lot of things are not directly related to the chip itself, but are consequences of the performance of the chip and have to be taken into account in order to develop something that at the end can be used. So we have decided to work on photoacoustics I just say a word about that. Basically, photoacoustics is the fact that instead of using an optical detector with a microphone. So of course, microphone, the interest is that the microphone is not selective in wavelength. So basically, any wavelength you use in your system, you're going to be able to detect with a microphone. So you use a laser, you send to the gas absorbs the light, it creates some sound waves, and then you listen to the sound waves using a microphone. So this is photoacoustics. You don't need a multipass cells, and you can shrink down the system without losing in performance. So when it comes to low cost, compactness, integration, that's a very good solution. If we are talking about very high sensitivity, extreme performances like sub-PPT or I don't know, that's not going to be the right choice. So it's really a choice for practical needs when you want to have a solution to a practical problem in the industry or in the environmental monitoring. So of course, the remaining challenge is the QCL, but this is what we do at mirSense. So here I just show you the product we've been developing, so MultiSense. So this is our product. So you can see here, maybe on my shirt, it's easier because there is not good. Yeah. See, this is very, I mean, it's a small sensor, I would say, compared to a 19-inch. It's 4 QCL inside, photoacoustics based, and you have a very nice interface where you can see the gas concentration in ppm this time is pretty fast, and it's the consumption is limited to about 10 watts. So I think it starts to solve some of the issues that were raised by Aamir. Of course, it's still limited, I would say, to industrial applications, where you can have something that is still a bit bulky, but even though it's small, but already you can think of portability, you can think of something very robust because there is no moving parts inside. And then the next step for us is that this is our first prototype of gas sensors, including QCL. So this is really in order for QCL to be able to meet some targets of replacing some already existing techniques in gas sensing. Because you have some techniques like electrochemical sensors, NDIR sensor, and PID. All of these techniques, they have their drawbacks. Electrochemical is usually drifting, but is very sensitive, and also can have some problem of linearity. NDIR sensor are usually very limited in terms of cross sensitivity because it's broad, it's a broad band, and also it's not as sensitive as laser-based spectroscopy. And finally, PIDs, they are usually have a lot of issue because you need somebody that is trained, you need some consumable. It's not selective if you don't add some specific consumable, so it's expensive and difficult to use at the end. So we think that laser spectroscopy can really solve this issue by bringing a QCL-based sensor that can solve all these different features. And of course, inside we have to put a QCL. So at mirSense, we do QCLs basically everything from 4 to 25 micron. And this is basically the technology that was used by Aamir in the 10 to 17 micron. By using a different material system, instead of indium phosphide, we use antimonide-based material. We can basically overcome the problem of absorption of indium phosphide that is a limit for making lasers at long wavelengths, and come up with lasers at room temperature, able to laser until 25 micron in pulse operation and until 17 micron in continuous wave. And still, the consumption is not crazy in the laser. You see in continuous here, this laser is about 0.6 amp as a threshold for a very long wavelength. So it's still really in the order of currents and voltage you can integrate in the system if you need these wavelengths. And that's it for me.
Thank you so much for this nice presentation, Mathieu. So here really we start to see the trend. So the trend is really the integration to higher level system. So we are really going out from the basic component level, but we are following this trend. Maybe if you could stop sharing, and then we look if there is any question in the room or comments on what presented Mathieu, and also comment on what presented before Aamir. Oh, okay, I don't see nobody is asking. Maybe I'm a little curious. Okay, now is the time really. Okay, just who raised the hand? Sorry, I have so
Slava,
Slava, go ahead, Slava.
I'm afraid to sound like a woodpecker, but question, you know, to Mathieu, really old one. Excellent family of solutions, excellent, you know. So as soon we are in very good friendly relationship with Alexei Baranov in Montpellier, you know, we are really looking that in the future, probably our range of spectra up to 16 microns can be upgraded to longer wavelengths, even to terahertz, because we have started last year to make our hollow waveguides, and they can match in general any wavelengths. But what I really want, my great wish, you know, to marry our fiber optic solutions with your lasers, because then you can really combine several QCL by 3 fibers, 7 fibers, what else, it depends on application, into this single fiber optic probe, which can go into, again, reactor, pipe, exhalation monitoring. So that's why here I really would like to follow after this meeting, Mathieu, by a kind of pragmatic action plan. What should we do to make the first prototypes running? We have already a successful start with Johannes, with nanoplus, but we are fiber optic bridge manufacturer, and we are happy to collaborate with all, with mirSense, Alpes laser, and so on. So please don't disappear. It shouldn't be only my wish. I hope you are interested as well.
Yeah, thank you, Slava. Yeah, I think basically the question of the fibers, I just comment on that. Here, I've shown basically local sensors. So, of course, local sensor will be dedicated to application where you basically can put your laser in the same environment as where you're sensing in general. So, and if you want to reach out for more complex and maybe harsh environments, fiber seems to be a very good solution. Right now, we have indeed it has to be found out what are the best applications to target with fiber lasers, and also to solve the problem of making low-cost fiber lasers, because at the end, fiber should not be too much an extra cost. So that's why we start working on that. And indeed, Slava, I will come back to you, because right now we are active on this subject.
Yeah, I can give you only one example. You know, years ago, we were invited to join project with Reno and Delphi in Luxembourg. Task was really development of engine, pure engines. Similar project was in Torino with Fiat, you know. Guys were trying to collect exhaust gas in resin pillows when they push the gas. When I arrived to Delphi and saw thousands of these pillows, I said, what are you doing? You know, they said, we should collect every second, you know, gas composition from the exhaust pipe. Now, with quantum cascade lasers and fiber optic access to exhaust pipe, you don't need it. You can measure very fast, you know, what is changed when you push the gas. You can help to develop, let's say, pure engines, even when we shall change, let's say, diesel to hydrogen engines. Hydrogen sounds good, ecological. Guys, it's not only water coming out, it's much more NOx toxic components coming out from hydrogen engine. So that's why, and we must control it. So that's why we have really good topics with you, Mathieu, you know, to go. Plus you are sitting in the area where a lot of, let's say, clinics are sitting, where the exhalation monitoring, even COVID can be detected if we shall control molecular composition of exhaust, of exhalation of the person. And it will be much faster than PCR. You know, we can detect it in the frame of airport.
Sure, sure. And I think that maybe I raise also another point for all the people in the room. Maybe we have also to think somehow on some standardization of the connection of the fiber to the laser. So as said Slava, just to connect the fiber to any laser. Maybe we can also do something that is going behind the standard SMA connector. That is not the best one, but something that is more useful to interconnect the laser and the sensors.
No, but with Mathieu, I agree that, of course, we should find only the applications where without fiber it's not possible. Because just imagine exhaust pipe, you know, nobody would like to put optoelectronics directly in exhaust pipe. So that's why it must be something, and plus we should think how to clean optics, because it will be contaminated on regular basis. We need some kind of process interface cleaning of optics, but this is pragmatic stuff. That's why what we need altogether, end users.
Altogether, that's the great magic word. So
Yes.
altogether, I would like also to give the word to Stefan from Spectragon. He raised the hands. So Stefan,
yes.
what is your mind?
Thank you, and thank you for a very nice speech, Matthew. And I'm just curious. I'm from Spectragon. We're manufacturing optical components, especially infrared filters for different application, among others, gas analyzing and gas detection. So my question is, using lasers for gas detection and gas analyzing, are you at all in need of optical components such as optical filters?
I would say in the first view, I would say no, in the sense that the laser is a spectral filter, in the sense that the output of these lasers, they usually tend to be in a very thin. However, maybe for application where we don't want to use Fabry-Perot DFB lasers, but may use Fabry-Perot lasers, but high brightness, maybe a filter could be a way to have cheaper sensor at the end. So that could be a path to follow.
Okay. So if you're in any need of anything, you know what to look for.
Thank you so much. And then, okay, I see, I missed the name, but I see the gentleman from Invisible Light Labs. I missed the name.
Niklas.
Niklas.
Yeah. Well, also, thank you very much for inviting me to also be part of this incredible meeting here, first of all, and also thanks for the talk so far. I really enjoyed it. We are a very young startup working on the first prototypes that we hopefully can have by, well, let's say in maximum 2 years. And I just wanted to also have a direct comment to also Aamir, Farooq, this first talk, and also to Mathieu, that we are currently working especially on detectors which are not limited by any wavelengths. So the sensitivity should be all the same along the entire electromagnetic spectrum, starting from the near infrared. So if there's some kind of need, specifically because in the talk of Aamir, it was highlighted again that the industry needs the detection anywhere, everywhere, and also in specifically maybe without cooling, so cost effective, that this might be interesting also for this community. That's why I just wanted to drop this here, also seeing the mid-infrared lasers here. It's very interesting, so thanks.
Yes, and please keep in touch, exchange messages here, and if after the meeting you need also to be introduced to anybody that you missed during the meeting, feel free to contact me or Francesca, and we are more than happy to introduce, because this is really the reason of this meeting, business opportunity, cooperation opportunity. And
thank you very much. Yeah, that's great.
Okay, Marek from Vigo Ventures. That is a new entry. What is in your mind, Marek?
Hi, Antonio. Hi, guys. Thank you very much for having me here. I don't want to sound as like a broken record, but talking about the things that also Aamir mentioned about the needs presented by certain industrial players or certain market verticals. From one side, it's from a point of view of an investor of having a formulated investment thesis. We need to have in mind not only the challenges on the deliverability of a certain solution, because within this group here, I can imagine that we could solve virtually any problem when it comes to the challenges of detection and of finding answers for the industrial players. The question here is to understand from the side of mentioned Saudi Aramco or others, what are the drivers that make them look for these type of solutions? What have been they using up until now? And how a proposition of using MidIR spectroscopy or miniaturized solutions will resonate with their long-term business proposition. And it's as I said, this might sound as a very basic approach, but we see a lot of times speaking with companies at different stages of development that this is omitted more times that we would like to, that a focus is made on truly finding a way to solve a certain challenge in the detection realm. But on the other hand, then we're trying to look for a business case afterwards. So it would be highly interesting for me to understand both of those sides that were mentioned, for example, by Aamir. So the needs, but also the drivers. So how the companies are defining a business case for them of why would they like for this to be introduced. Is it legislation? Do they need to comply with some changes in the legislation, or is it something that they're looking for savings on the production or others? This was on my mind. Thanks a lot.
Thank you so much, Marek. I think that you pointed the finger on the right direction also, because at the end of the day, the success is driven by the customer, the end users, but also we have to understand which is the driving factor of the end user to adopt or to not adopt some solutions. Mathieu, you raised the hands.
Yeah, I wanted to try to bring some kind of answers to the question, and indeed that's partially what I try to emphasize in my presentation, is that we don't do a sensor to make a sensor. Basically, we try to answer to the problems and limitations of some technologies, and I think benzene is a good example in the sense that right now, basically we are in contact with quite a lot of companies looking for a benzene selective sensor. And at the end of the day, right now there is an unsatisfaction on the market, because on the one hand you have big analyzers like Chromato to detect benzene, which are expensive and very bulky and very slow. And even if you use some optics, you can get laser-based detectors with limited performance, can be enhanced by using the wavelengths we've developed. But at the end, still you don't have something that you can put on each of the workers, and that will prevent them to be ill and to have some issues of health at the end, because benzene is known as a bad molecule. But since there is no technology right now, basically the workers affected by benzene are in a dangerous situation. So we definitely decided to move to benzene because of that, because there was this need, because the company asked us for solutions how to measure benzene, which can be low cost, with no consumable, and can be used like it's done for H2S. And H2S is pretty much well fulfilled. We don't care about H2S with our lasers because there are solutions. However, there is no for benzene. So I would say this is typically a driver for us from a market point of view.
Thank you so much. And Aamir, you raised the hand, please.
Yeah. So a comment and maybe a question then to Marek. I think that's an excellent point, Marek, you made about the business need and why should companies invest into it. But fortunately, I don't have to worry about that question. I'm in academia, right? So if a company comes to me and says, here's a problem, I just tell them, give me this much money, right? Give me the funding, I'll do the work for you. And then they worry about the business case, right? Or you guys worry about the business case, right? But in general, I will say that, the needs could be different. For example, with Saudi Aramco, many times we are looking at process optimization. As you said yourself, maybe saving something on the production side, right? So many times they tell us that they've been doing sampling-based analysis of, for example, the natural gas they are producing, right? So, for example, Saudi Arabia, they didn't care about natural gas before. They were just producing so much oil that was enough, right? And now they are putting more effort into natural gas production to some extent to convert it to hydrogen through SMR process and then make blue hydrogen through that process. And now they have to worry more about their natural gas quality and online monitoring of it. So now they're saying the lab-based, sampling-based approach doesn't work. Now we need more online monitoring of this. So we need more advanced and online kind of monitors for that. So that's just an example of the need that's appeared. My question is for Mathieu on photoacoustics. So there's this feeling in the communities that the photoacoustic senses can be affected by environmental factors like temperature fluctuations, maybe some noises and all of that. And I know you targeted a specific frequency for that, but have you really tested it across environmental changes and it is immune to that?
Right now, we have already sent some modules that are commercially used in some installation where they are responsible for measuring inline process or ambient air quality. And so we've been solving the issue of external noise. So basically, we are able to bring the external influence below the noise level of the microphones. So we are limited by the noise of the microphone themselves, which basically are some Brownian noise from the membranes. And concerning the environmental changes, of course, you're right that one of the drawbacks of photoacoustics could be that if you change the gas, you change the velocity of the sound. You may change even some effect of desexcitation of molecules inside. When you excite them with the optics, they have to desexcite in acoustics. And these effects we have taken all into account in our company. So we model that. We have all the firmware and software. So now we are pretty much free of problems with the photoacoustics.
Yes, sure. And yeah, it's really becoming hot, the discussion after two speech. I see that also Richard Crocombe raised the hand.
Yeah, thank you. Just a couple of thoughts. It might be worth looking at the technologies deployed in the safety and security sector. There are wearable ion mobility spectrometers that are widely used by the armed forces that are pretty selective and very sensitive, and will be sensitive to the sort of gases that are mentioned here. And again, in that sector, there are very small portable FTIRs made by companies like Smiths Detection and Thermo Fisher Scientific, and they've solved the size, weight, and power and environmental problem. Now, these are low resolution devices as compared to lasers, but if you're dealing with heavy molecules, sometimes wider wavelength coverage is much more valuable than resolution. So I just encourage people to sort of take a look at what is used in the sensing and detection devices in the safety and security sector. Thank you.
Thank you very much, Richard. Thank you. Thanks a lot. And maybe now we have still maybe some comments from YouTube, but it's better if we go on and then we bring it up later. Actually, it's on FTIR, so that is a good point. We take this topic again later. Now let's go to the detection side. We were talking so far about all the mostly active part and end user. Now it's time a bit to give the floor to the boss of Marek. So it's time for Vigo Venture and from Adam. So Adam, welcome to the meeting. The floor and attention, everyone, goes to our also freshly new member from the board of EPIC. Adam, the floor is yours.
Hello, can you hear me?
Yes.
And
we are about to see your screen. There you go. The floor is yours.
Okay, so I will go very rapidly through the presentation about Vigo, since we're pretty well known in again, it's the same problem. So
we can see the first slide.
Okay. No. So Vigo is on the market since 34 years, but actually we speed up with development in the last 4 or 5 years, and it was a response from our investors since 2020. Because there is a lot of happening in MidIR, and we are seeing is that the market is growing, that our products, infrared detectors, but also the materials for infrared detectors or more complex systems, infrared modules are finding new applications. And it was great to listen to Aamir's presentation on the requirements, because it's actually our roadmap for making the devices low cost, sensitive, and affordable, available for different environmental requests. And in our business model, we are trying to connect different areas, talking to the competitors, to the different technological providers. That's why we created Vigo Ventures, that already backed 6 startups to really support R&D teams on developing new technologies. This is extremely important, because there are so many different technologies for sensing applications in the market, both with lasers, with LEDs, with tunable diode lasers, and it's really fun to see how those devices are being used in factories, in open air, for air quality monitoring, or sorting garbage, or in pharmaceutical applications, but also in very specific applications on Mars, or in many different cases. Of course, MidIR is also temperature sensing, and we are using our detectors for safety of trains, and detecting of different hot objects, and MidIR is really a great area to discover both temperature, size, and the composition of the material. So we are happy to be here, and to see that this market is really growing. We are in Vigo, we are manufacturing everything by ourselves, but this is about to be changed. We are looking for partners to support us on different areas, both epitaxy, processing of the materials, packaging, and integration with other components, driving lasers, driving detectors. So there is a lot of things to do. We're really. I had the pleasure to be in San Francisco at the first physical Photonics West conference to present and talk with customers on new products. But it's really happening that new things are being installed into different kind of systems. But there are, of course, needs. So most of devices, as Aamir showed us, are really large in MidIR. They are very important for the society, for environmental monitoring. Many of the processes on our globe started with some MidIR sensing, like emission monitoring of some cars, or detecting CO2 levels in the atmosphere. That's really important. We had a great project on MidIR sensing in MIRFAB. We created a great community of people, and MidIR Alliance is a result of this cooperation. Happy to be with so many players that are adding to our core MIRFAB group, that we can work together. And next stage is to go from the handheld sensors to the finger-held sensor. That's really something that will create a new thing. At Vigo, we have an internal national project on mid-infrared photonic integrated circuits. But the main driver is really price and volumes for the applications. We used to concentrate on industrial processes, environmental and protection applications, but the medical technologies, consumer electronics, Internet of Things is a totally new market for MidIR, and will be a great cases for everybody of us to learn, to introduce the two technologies, and we have plenty of things to develop, to create really MidIR photonic integrated circuit, and there is no one that could do everything. We at Vigo, but also our partners from all around the globe are looking for solutions, for support, for different components, for creating the photonic integrated circuit service stack. Really, peaks are something that is part of important projects for common European interest. It's part of the CHIP Act for European Union, and hopefully this will be a driver for growth of our community in near future. So thank you for your attention, and hopefully that we can work if we are looking for some support. We are looking for these areas to grow and to cooperate, to have input, and to support a great system integrator like Aamir to really provide end users with their solutions. So once again, thank you for your attention, and that's a part of the areas where we are looking for support.
Thank you so much, Adam. This is very fine presentation. So here you put on the table really the challenge to go further with the integration on photonic integrated circuit. And here really we are going on not on a single platform, but really here we are going to a hybrid platform integration, because here we are speaking about waveguides, QCS, and other laser devices as well detectors. So here really you are setting the route for the next years and tens of years for the development. This is really great.
Yeah,
and
yes, we are opening discussion for how can we work together inside of the MidIR Alliance to really share the knowledge, share the experience, and create a really independency of technological sovereignty of Europe with the sensing.
Yes, sure. And yeah, I see that Aamir for CSM raised the hands, and then also Slava. But first, Aamir.
Yeah, can you hear me?
Yes, sir, please.
Yeah, Adam, thank you so much. This is a fantastic presentation. I'm really looking forward. I mean, at CSM we've been also trying from a different angle to actually push toward mid-infrared. Maybe I make a little sort of a introduction presentation. We are working on a new platform called lithium niobate and insulator, which is a nonlinear platform. So frequency down conversion, sort of people have been generating terahertz since ages, using the frequency down conversion. We actually got our hands, also started to thinking about actually doing it, toward the mid-infrared, using just a down conversion from 1550. I mean, just this wavelength conversion is something unique into lithium niobate. I don't know if you see any sort of a room for such a modules actually, whether actually we down convert to generate or up convert, and then using Aamir for silicon photodetectors, which is the best photodetectors you can ever find. So I think that's this sort of adding in this nonlinearity building block to this is great. But for me is that, so what is a key, let's say, platform that you're going to use for such an integrated circuit? Because we have glass absorptions at mid-infrared, which is really killer. Silicon is not super transparent, above I think it's above 5 micron. So what do you have in mind as a base material for waveguides?
So currently we're looking at silicon nitride, but also we are looking for different other materials that even germanium that could be used as a waveguide. We're really open for testing different areas, different platforms, and even silicon itself in some areas might be good for providing us.
Out of curiosity, what wavelengths range are you talking? Because sort of silicon nitride core with such a small refractive index at 5 micron is really hard to confine light. And
so all the MidIR always started with the measuring of the process gases, like
1.5, 3,
nitric oxides or methane, and those are the monitoring of the process gases usually needs a wavelength up to 5 microns. Above the 5 microns is really those heavy compounds, and for those platforms we are looking for future collaborations, and after integrating the up to 5 micron, we can test other platforms. Maybe also the down conversion might be one of the solutions to really make a component in that could somehow translate through the wavelengths.
Yeah, I'd love to follow up on this. Thank you.
Thank you. And Slava, go ahead with your
comment. I have one, happy question and congratulations to Adam, because I think Vigo found kind of, let's say, a golden key to success for the development. And this key, I just remember, father of Adam, I'm old guy, so when Vigo was starting just to make detectors, and now it's a complete system. So that's why congratulations, because you decided not to wait when system integrator will come to you, and you started to make complete systems yourself. So jumping from B2B level up to B2C. So it's great. To be honest, we are maybe 5 times smaller than Vigo today, but we have at least similar intention, you know, and that's why my, how to say, a bit sad question, because we have excellent communication a couple of years ago at Photonics West, you know, and then it was great plan maybe to start something to do together, because I didn't see in your slides any, let's say, small piece of slides, you know, devoted to fiber optic, which is available for mid-infrared. Can you comment on it?
Yeah, I'm continuously a fan of fiber optic based sensors with some scenarios where fiber optics can be used, but I was happy also to see it on a list of requirements for Aamir. But there's in the MidIR currently most of the system integrators are based on free space optics on the large path. I think that going into the hollow waveguides with a hollow waveguide filled with gas, it was an interesting customer demonstration that I saw recently. That might be a great scenario to really have a very long path with hollow gas filled with gas. Of course, there are issues to pressurize the gas to put it into the hollow fiber. But all the other cases, I'm really looking for the customers, integrators, for the cases where we can really work together on some larger scale cooperation towards applications.
I see where we can help, Adam. First of all, hollow waveguides, they are on the shelf. So that's why we can simply start, you know, from any system, but you don't need a hollow waveguide only, you need a source of light. That's why, you know, source of light, we really did experiments with nanoplus QCL, with some other QCL. We have excellent coupling efficiency between hollow waveguides and our polycrystalline fibers. Simply the difference that a hollow waveguide has about a numerical aperture about 0.03, and polycrystalline fiber has 10 times bigger numerical aperture. So that's why it depends which application to provide. But in all your systems you show, it's clear that you do not manufacture yourself sources. So
no, we are looking. We are from the beginning. I'm happy to work together with all the brilliant engineers working on quantum cascade laser and interband cascade lasers. So it is.
Then we can bring, you know, fiber optic pigtail QCL from Johannes or from Mathieu, you know, just to complete your complete devices. So we'll be happy to do so. So let's talk after the meeting, you know, how to make pragmatic actions.
Absolutely. It's so important, because really fibers here represent the glue between sensors and laser source to the point of detection. So here we are really, I really appreciate if we can start working together to make this happening. And now I would like to see the comment from Sergio Nicoletti from CLAT. He was the coordinator of MIRFAB, so he's really our father of this technology, or of the father of this community. Sergio.
Thank you, Antonio. Too much. Yes.
You are not showing yourself. You are at Bermudas, or
more or less. I'm at home. Well, I can show myself. I am at home. Just move a little bit the screen. Well, yes. First of all, thanks for mentioning MIRFAB. It has been a great experience, and I was lucky to be the coordinator. And those who knows me already knows very well that what Adam just presented is what we were pushing within MIRFAB and what we are currently pushing at CLAT as a wave for the integration. Let me make a very short comment concerning the choice of the materials. Well, for the wave guiding in the mid-infrared region, I think the best candidate is still germanium. not only because of the manufacturability, but also because it fits most of the properties of transparencies in the mid-infrared range. This answers somehow the question from Aamir. But the reason why I raised the hand is a little bit different. What I've been seeing so far, besides probably what Mathieu showed, is the fact that we are almost looking to a high-end application where we have a sensor that costs thousands of euros or even more, or 100,000 euros. So I was wondering, and I don't know who can answer my question, if we have in mind application where the numbers are big enough to support volume production, because we cannot hide behind I would say behind our finger. There is always a chicken and egg problem. Today, the cost of the sources is too high because the volume are small, and so we have to cut or break this equation in which the cost is high, so we cannot address volume production. I guess there are many initiatives around the world in order to reduce the costs, but we are not there yet. So, well, I'm seeking for comments from the people.
So Sergio, you're
industrializations.
Sergio, you're fully right. Staying with the current applications, very specific medical experiments or very specific scientific experiments, or even process monitoring is not a large volume application. We need to go into the really monitoring of the areas, monitoring of the air, going into house monitoring. So generally, Internet of Things as a solution for that could replace the technologies that also Mathieu mentioned, the electrochemical cells and the IRs. That's the area where we could go. But of course, we need to be at the price level of few euro per component, and this makes the tough job to really integrate the whole system monolithically or with the hybrid integration, but all our price calculations show us that we are with the MidIR components. We can go there down to the few euro price tag, which is the limiting factor for scaling up. And as it was done with the microelectronics and what our founder of the TSMC show, it's always in the semiconductors, it's always you need to be in front of the income curve with the costs. So you have to invest into the new technologies and then get the result back. So that's why there is a chip act, there is a IPCEI on microelectronics, and that's why the photonics should be a part of those initiatives to really support the growth of a new technologies or scaling up the technologies to really overcome this hen and egg issue.
It is already part.
Yeah, it is.
If I can just make a comment, it is clearly that the market is the main driver. We have been making some calculation recently concerning how much we should charge a line in order to fulfill all the requirements in terms of sources. Doesn't matter which one it is. If the fabrication occurs on a 200 millimeters wafer, and we ended up providing work for a medium-sized pilot line, like for example, any of those already exist in France or in Europe, for like 1 day of work, which is not enough to sustain the business if we move to volume production. That was my comment.
Sure.
Sorry, go ahead. Aamir.
Sorry, I see Aamir. I see Aamir. They've raised their hands since a while, and then we have Slava, and then I recommend that we go to the next speaker, because really we are less than enough of our path.
Thank you. So actually, this is a sort of a follow-up, or let's say comment to Sergio. And Sergio, I cannot, I agree with more than like more than 100% with you that actually it's the cost and the volume application that doesn't exist in MidIR. It's a challenge. And coming back to your like germanium, indeed, germanium is a perfect material for the MidIR for waveguiding, but the problem is which foundry is offering it, right? Well, so it's again a chicken and egg, because like any big platform that doesn't have application in telecom, or I mean, I have a very pessimistic view that it never flies, right? You can maybe do it in a lab or something, but there is no foundry, because the reason that actually we have silicon indium phosphide is purely because we have telecom market, and they are driving down the R&Ds and the costs for doing it, setting up, and then maybe other wavelengths benefit from it as a secondary target. But MidInfrared is not a big enough market that you develop a germanium integrated photonic foundry.
Can I answer? Can I answer, Antonio?
Yes, yes. Sergio.
Well, it turns out that the germanium is in many foundry today, more than lithium niobate by the end.
Absolutely, as a detector, not as a waveguide, right?
Sorry?
As a detector, but not as a waveguide. I mean, you have germanium silicon, but not germanium pure waveguide.
You have germanium. The only problem that I can foresee now is the thickness, which is slightly different.
Exactly.
But at least it's more known. Is more, I would say, easy to introduce germanium in a silicon foundry than any other material.
Sure.
That's the opinion. That's what we are experiencing every day. But let's not go too far with the discussion.
Here we are really going into very deep tech. Slava, what is your mind?
Very shortly, Sergio really raised very important question, where mid-infrared photonics products are needed for high volume. And I think after good investment of mirFab and many good partners there, question, is it any commercially available product available after that mirFab platform? Anything which end user can buy? Sergio.
It's not me to answer, it's the industrials.
Not some members, okay.
Yeah.
Vigo,
I think my point of view is that my way to see it is that mirFab was not the unique driver, but those companies that were involved in mirFab, at least I saw them progressing a lot. Of course, they did a lot of work independently of mirFab, but mirFab was one of the helping factor of their successes.
Right. I agree that progress was reached. Question if it's reached some kind of critical point when thousands of devices are really requested for sale on the market. That's why here I will not ask for the question. It's a very difficult one, but what I think, what is really important for all of us, market will appear as soon we shall know the problems. If end user has somewhere problems which they could not solve, without our fiber optic mid-infrared devices, then we should talk to them in money language.
Yes, sure.
And Saudi Aramco, for example, petrochemical business, biofermentation, bio-waste. Today, if you look how many calls from Brussels comes for the new projects, 8 calls with a deadline in April for soil health and food. So that's why if we can provide something for that direction, at least for the projects to develop low-cost devices. So because all of us would like to eat, let's say, healthy food and to be healthy in general, so that's why this is life science, maybe one of the major markets.
Yes, sure. This is a very interesting discussion, but now I'm sorry to stop you, Slava, but really we have to go on. And so now I want to give the floor to Johannes from nanoplus. They produce a huge range of wavelengths. Johannes, the floor is yours.
Okay, Antonio, thank you very much. And thank you very much, EPIC, for the opportunity to present our sources here. And it goes into the direction of lasers, but not only lasers, I brought a little bit more we have at the moment. So in principle, next page. We have 5 pillars of products. The first one, also mentioned already here, are DFB lasers, and we can cover the wavelength range from 760 nanometers up to 14 micron with different technologies like diode lasers, interband cascade lasers, and band cascade lasers. And we also provide their customer-specific solutions. So if you have a special need for a special wavelengths, let us know. We make it, and you get your laser for your application. Furthermore, we have hybrid power laser diodes, also covering the same range. Up to 1 watt CW output power comes out of these devices, and you can use them for cutting, welding small things, or combining several and do really high power applications. And then we have, and this is perhaps not so well known, SLDs. And with these LEDs, we cover the range from 760 nanometer to 3 micron. We offer them CW at room temperature, and they have this broader emission features. And I think, especially in liquid sensing, there are some applications where they could be the weapon of choice, really to solve your problem. This is perhaps then your light source in combination with the detector from Vigo, for example. Furthermore, we have the mid-infrared LEDs from 2.8 micron up to 7.5 nowadays. It's an update, at least in the lab already. And I think these LEDs could be the key for high volume, low cost applications, which are deployed in some fields, or you have a sensor covered with you in a point detector kind of thing. So I think these LEDs really can address the mass market. Furthermore, and Slava already mentioned it, we have customer packaging. Here you see a package we developed for QCL fiber coupling, I think, just as one example where we did development of technology for a specific need. So our lasers, here again, the overview of the different technologies we can provide, of a large tuning coefficient, have decent amount of output power. For gas sensing, normally you don't need watts or hundreds of milliwatts. You just need a few milliwatts. We provide customer-specific packaging solutions. You can see some of these examples down the page, where we have TO5 packages, we have butterfly packages, Q66 packages. And we also provide accessories. If you want to have something for your lab for first test, we can provide cages for this. Here are some examples of typical lasers we bring to the market: 760 nanometers for oxygen sensing and 1877 nanometers for water vapor sensing. You can see very nice lasers, threshold around 10 milliamps. So you can really use them in portable devices which are battery driven. The laser is not the main user of power. They are very efficient. And they also can be tuned quite good with temperature and current, so you can really adjust the laser to your wavelengths and then scan above the wavelengths with the laser. It's very nice doable. At the right corner below, you see a typical absorption feature of water vapor when you measure in the lab ambient with these 1877 nanometers laser. You see the dips in the IP curve, and they are due to water vapor absorption. So you can make a simple water vapor measurement in your lab when you characterize the lasers. So in principle, we can address all these gases like N2O, CO, NO, HF, HS, H2S, methane, ethane, propane, butane. All these hydrocarbons are addressed by our interband cascade lasers. And I think in future there will be very exciting applications around this. And we can offer the light source for this kind of applications. So here's one example of a 1 watt laser at 2.1 micron. You can use them, for example, for drying wood. This is one example I know from one of our customers, or cutting into patients. So different options for the use of these kind of lasers. We can also offer them as a bar, so you can combine the lasers into one fiber, for example, and do cutting and welding applications. Here, our luminescence diodes covering the range from 760 nanometer up to more or less 3 micron. Again, we have different package options available, but for details, just look on our webpage and you find the spectra and examples of diodes we can provide there. But always keep in mind, if you have a special need for a special wavelength, for a superluminous diode, for a laser, for a Fabry Pro high power laser, just let us know. We typically can provide the laser. And last but not least, I show here in a mid-infrared LED with decent amount of output power. We are the first company providing CW 2 milliwatts output power at this wavelength in a LED. You can see the emission is a little bit broader. You can, for example, test for liquids, or you can do a photoacoustic absorption measurement with this kind of LEDs and detect something in a point detector, very efficient with low power consumption and low cost in the end. Yeah, this is all I want to show from our sources, and I'm open for your questions.
Thank you so much, Johannes. Yeah, I see that there is no hand raised, but I think that there are some questions from YouTube channel, Francesca.
Yes, thank you, Antonio. So our friend Mathieu, another Mathieu Besonneuve, from INO in Quebec, asked a question long ago. Then maybe we can address again back to our spectroscopy experts. So Aamir, the question was to you, but we had to pause a bit the flow of questions. So we mentioned already a bit also, Richard did it before. What about, in your opinion, the application of this technology in more standard spectroscopy tools like FTIR or Raman spectroscopy? What is your feeling at the moment in the MidIR sector for the application there? Is there some challenges you see that there is a future, there is maybe not a future anymore? Some hints for us. Thank you.
Sorry, is that a question for me?
Yes, Aamir. Okay. Yeah, just from your experience, like as a spectroscopy master.
Yeah. I think for spectroscopy, there is more of a scientific need, and I love doing that work as well. I think there you need more, more precision in your measurement from both the x-axis, the wavelength axis. So you need a really high accuracy on your wavelength, and then also on the y-axis, if you want to measure the line strengths, for example, or the broadening coefficients, also those are needed. So for all of that, I think the tool that has really come about in the last few years is the frequency comms, right? So the frequency comms are really fantastic tool for doing high precision spectroscopy, and their expansion into the MidIR is happening, but is still not at the same level as what you can do with frequency comms in the near IR. So that's definitely for the MidIR community, something that I know many people are working on it, on extending the frequency comms towards MidIR. But that's as that happens, I think that will bring about a lot of really cool high precision spectroscopy work in the MidIR. So that's a tool that I'm really excited about and plan to use as well for spectroscopy work.
Very good, very good. Then I guess in the network we have enough people and enough companies that can maybe think about this. And even if they are not here, I'm not sure. I guess not all the interested one are here. Definitely, we have enough in the network that could support you, and maybe also talk offline with you, Aamir, about the expansion towards MidIR, because we had also some past event about it, and there is something going on, and so be aware of this. Yes. So maybe it's now time for the comment from Ian from Vortex. Ian, please take the floor.
Oh, hi. Thank you very much for having such a wonderful meeting here. It's very interesting to hear what's going out there. I had a question for Johannes following the talk just there, and it was noticeable that the infrared diodes, the infrared LEDs had quite a broad range to them. And what I wanted to know, was there any scope there for working to particularly cap those LEDs with a filter to try and tune it to a particular gas? We've got a lot of experience with this. Is it okay if I show a quick slide? What? Okay.
Totally, absolutely.
Yeah, okay.
Go ahead.
Let me see. Bear with me. Has it come through yet? I don't think it has.
Still black for me.
Yeah, it's black for me as well. Let me try again.
It was like it was taking a while, but maybe try again.
Yeah, try.
Yes.
Okay.
Just keep it there.
Yeah.
Okay,
your last slide. Go back, actually.
Go back to the last slide.
Go just to the normal
it,
view.
yeah.
Okay. No, there it is. It is there. It is there. It is there.
Yeah. We'll go back to the beginning. Yeah. So the company's Vortex Optical Coatings, and we're a specialist in making filters and beam splitters. And the picture in the bottom right hand corner of the screen is the sort of classic way things are detected. So this applies to NDIR, where there's a light source and then a detector, and then the filter is in the middle there to try and give this useful bit that for the gas or the plastic or whatever it is you're looking at. And also in these systems, there'll be beam splitters and dichroics, usually used for sectioning off certain parts of the spectrum. So what we do, or what we've proved to be quite good at, is making prototypes for these, because there's been a lot of focus on cost today. It's been mentioned quite a few times, and normally there's not huge amounts of money flowing around in the early stages of developing a system. So we've got the ability to do it quickly. Okay, also with our experience, design it to actually do what the customer needs. And then the other thing that we bring to it is we're well set up to do it with low cost as well. So as far as what people can do for us, I do like these forums because it's a great opportunity to share knowledge and for us to learn what's out there. It's also a great opportunity to see what challenges are out there as well. And if people are interested in developing detection systems in the MidIR, we'd be a good partner for that, simply because of our ability to do these things quickly and at low cost. And that's by my contact details down there. I'll stop sharing because I can I wanted to ask the question about the ability of these LEDs to be used for tuning particular gases to Johannes at nanoplus.
So I'm quite convinced that the combination of your filters and our LEDs could be very useful for applications, because you have an additional degree of freedom to limit the spectrum and to make a measurement. And I think in this combination you can make a better resolution system out of simple LED detector scheme. And I'm quite optimistic that there will be applications for this.
Yeah, it's often used in the visible, and the way it seems to me is it's moving into the infrared now with the manufacture of good quality mid-infrared LEDs.
Yes, definitely. This is a driver, and you have to think of also hydrocarbons you have in the mid-infrared range, which you can address with light sources and detectors in this range. And there's a lot of work to do. I'm very sure about that. If you think of food and agriculture, there are a lot of things you want to measure with fungus or in the medical area. So there are many fields where we can altogether provide solutions to this. And perhaps the combination LED and filter is a good combination for a low-cost, mass-produced sensor.
Johannes, what is the price difference between intercascade lasers and LED for the same range? About 10 times, 5 times?
It's depends strongly on the volume, but it's 5 to 10 times.
Okay, thanks.
Okay. So here really going to the business and really going to concrete solution. And I would like now to introduce Samuel from Verre Fluoré. We've spoken a lot, we discussed a lot about fibers, and now we listen from Verre Fluoré what is also coming from this and how we can integrate and use more fibers. Samuel, you are muted, I
Hello.
think. Oh, great.
Hello, everybody, and thank you for the opportunity to talk in this meeting. You can see my screen?
Sure.
Okay, thank you. So, first of all, I will present you the fluoride glass on fluoride glass fiber components on products for Mid-Infrared Alliance. So, first of all, we are talking about fiber for transmission, transparency, especially from 2 microns up to 5 microns. And also, we are talking about light sources because we've got many rare earth transition in fluoride glasses and more fiber laser are now commercially available. So concerning the passive fibers, so we can use, depending on the need, some multi-mode fiber just to transmit mid-infrared light from backscatter light, for instance, but also for mid-infrared laser delivery for small power up to significant power, and if needed, we can change the glass in order to handle very high power. But I guess this is outside this event, talking about high power lasers. We also can propose some fiber for single mode light delivery, especially for ICL and QCL pigtailing combining. And I want to highlight the fact that in this event, we've got mainly 2 mid-infrared fiber company, Verre Fluoré and Photonics, and we can see that there is a very high complementarity between both technologies that can allow Europe to propose by far the best solution from 2 micron up to 15 micron. The association has a great potential, especially for ICL and QCL pigtailing and combining. Let's talk about light sources, because with rare earth double cut fiber, we can make many kind of light sources. The first one are more dedicated to medical application or to material processing, but the 2 latest one can be of great potential, because mid-infrared supercontinuum light sources can be very useful. And I cannot disclose all the details, but we found we are digging a rather significant business using this technology. Moreover, the latest one, we can grace off our erbium dysprosium coated fibers, make some tunable fiber laser. And there is a sort of publication or scientific talk in a Mid-Infrared Alliance website And this kind of light source has to be developed, and we are already in discussion to develop this kind of broadband light sources. So what can we do for EPIC? What can all the partners can do for us? We are talking about developing new light sources, but also integrating mid-infrared light sources for material processing and also OCT, optical coherence tomography, which is of great potential also. Latest point, fiber components, because if you want to integrate some solution for industrialization, you need this kind of components like flow cells, hermetic fish-through, fiber bundles, and this kind of fiber bundle dedicated to ICL and QCL fiber combiner. And once again, those technical solution can integrate all kind of mid-infrared fibers, and especially our photonics fibers. So in terms of cooperation, we would like to work on integration, on improvement of our products in order to reach all the targets that have been mentioned, reliability, cost, and so on. Thank you.
Thank you so much, Samuel, for this too short explanation. Frankly speaking, each of you has to explain a lot of things, and especially for me, that is coming from laser, that is amazing work. So, anybody would like to comment on the presentation of Samuel, or anybody from the laser side? Johannes, Antoine, that will speak later. Mathieu? Okay, I think that I feel that we got so many information that maybe sometimes it's also necessary to take a breath. So I will give the floor to Antoine, that is a laser man, is a laser specialist. So maybe we can develop more also the concept about how to integrate a laser with the fibers. One, you are muted. Okay,
yes.
Full screen.
Can you see my screen?
Go.
Okay. Thank you, Antonio. So we'll give a few words about Alpes lasers. So Alpes lasers is a former spin-off from the University of Neuchâtel. We spun out in '98. And at this point, we have started mostly commercializing the QC lasers that were invented by Jérôme Feist and co-workers at Bell Labs. And so Alpes lasers has been working in various configurations. Now we're about 30 people. We're mostly working in a fabless situation. So we're having the fabrication processes done outside, and we're mostly doing packaging, like the back-end activities and quality assurance in-house. So we're concentrating in the mid-infrared. We have in the very far infrared terahertz QCLs that now are reaching Peltier temperature. We have QCLs, we're working on ICLs, and we have diodes. The main usage for our devices are essentially around two axes. On the one hand, the chemical sensing. As we've seen, we can detect gases and also larger spectral features such as substance diluted in water or solids. And on the other hand, we have a strong activity on energy deposition. Mostly this time, instead of using the absorption of the atmosphere, we use the fact that some regions of the atmosphere do not exhibit too many absorptions, and so that we can convey light onto, for example, the sensing head of a missile and jam it. So this is the other arm of our activities where we developed high power devices, 1.5 watt and more, in a very rugged configuration so that they can fly and sustain the various difficulties that can occur in a military platform. So in summary, the components we're selling are mostly DFB lasers that for gases, Fabric Pro devices, mostly for as gain media for external cavity devices, where a large tunability can be reached, which is pretty nice, for example, for measuring these broad spectral characteristic substances, the high power devices and terahertz devices. And then we have also the same for ICLs and laser diodes, where Then we have also a line of electronic drivers for the different type of lasers, temperature controllers, and also all the electronics necessary for external cavity controller. And also we provide options with pigtail devices with essentially any kind of fiber optics. And also we can develop custom systems and provide also component development and system development, or all the way to research on hire. I'd like to show one of the latest results we got in comb development. We've been working quite a bit on developing QCL combs. So this is not a device that is pumped and provides the comb as a side effect of the high power. It's directly generated inside the waveguide of the QCL. So we design waveguides where we engineer the dispersion, the chromatic dispersion in such a way that the spacing between the modes of the Fabric Pro modes that you have inside your waveguide are exactly equidistant, so you can have the buildup of a nonlinear effect that will create a coherence between the different teeth. And on the right, you can see the resulting beat frequency that you can measure when the device becomes calm. And you can use that to do spectroscopy pretty efficiently. And you see we have a very large part of the dynamic that is comb operation. As I mentioned, we provide services from the dedicated component design up to integration, and we also do this through either direct investment from customer or in collaboration within EU project. And this is a few of the fields in which Alpes Laser is active, from nutrition to water quality and first responder protection. And for example, the combs project, which is a result where I just shown a result of our activity. We presently have 16 active EU grants ongoing. A few of our customers, and I guess I'm out of time. So thank you very much for your attention. I will stop.
Thank you very much, Antoine. That is really interesting. And I think that, yeah, also your project looks very interesting because they touch also something that are extremely important, water and food. So this is probably a challenge for us, for the environment, for circular economy. But here really we are touching water and food. So this is a global challenge. I see Aamir that raised the hands. Aamir?
Yeah, thank you, Antoine, for the presentation. I have two questions. One, we heard from the previous speaker about the fibers available in MidIR. So do you as Alpes plan to offer fiber coupled QCLs and especially DFB fiber coupled QCL? Is that on the plan? And the second question is about the QCL comms. From what I understand, these QCL comms have relatively large spectral sampling compared to the frequency comms that you get from mode-locked lasers. So is that limitation something that you think you can overcome with your further development?
Okay, so regarding the question of the fiber optics pigtailing, this is something we're active on. We have been successfully pigtailing shortwave, midwave devices, like in the 4-5 micron region, using le Verre Fluoré fibers with much success. We've been also working at longer wavelengths, and the technology we're using is compatible with this kind of challenges. So we can essentially offer any device that can be used on driven on Peltier cooler with a fiber optic. Now, regarding the question of the comms, indeed the mode spacing in a comb will be in the order of a fraction of a wave number, like one wave number, half a wave number, and up to a quarter of a wave number. But it becomes difficult to imagine closer spacing, because that would really make a very long device. What you can do, however, is that even, for example, working with dual comb spectroscopy, where you need to synchronize two combs pretty precisely, you can sweep them in temperature, and so that you can move each teeth in parallel, and then have a completely continuous spectrum then that you can measure. There is an article by Hugi, I think, from IR Sweep describing this effort and this kind of measurement.
Okay, thank you. Just to follow up on the first, so are these fiber coupled pigtail devices, are those custom devices, like a customer have to come request to you, or you're offering them off shelf like you have your other DFB lasers?
We try to offer, I mean, we have options for the short wavelengths we offer and we guarantee. And then if the customer wants to use a special fiber he has, or he has special needs, then we will study together with the customer how we can do that and what can or cannot be guaranteed in this situation. But we're pretty flexible.
Okay, thank you.
Great, thank you so much. And Samuel, go ahead. Samuel from Verre. This is a comment.
There was a question about the development of fiber solution to couple or to combine in the single mode way, because we're talking about single mode, which is very important. So yes, there are some developments about it. Some of them require a unique kind of glass because it's a fusion spliced solution, but others are compatible with different kind of glass technology, which is very important, because if you want to make very specific measurement, maybe you would require a 13 micron QCL and a 4 micron ICL. In this case, maybe the optimal solution should be a mix of different kind of technologies. So like always, depending on the needs, there are some kind of solutions, but they are not, as I know, validated for industrial uses. Unfortunately for you, you should wait for No, I should say 1 hour, 1 hour and a half for that.
Okay. So sure, that's the problem. So here we are going also to go, depends from the application, also the way to put together fiber sensor and the laser. So here really we are going again from the beginning. So we have to follow the application and the user needs. And here I see that also Luca from Enea, Luca Fiorani from Enea is a
Hello.
researcher, but also an end user. So tell us, what is your mind, what you are asking now, really,
Yeah.
at the end of this meeting?
Yeah, my question is exactly about end users. And you mentioned an application in a food project. Can you tell us how have you applied your lasers? Some more details in this food project.
You're asking to me?
No. Alpes laser.
Antoine.
Antoine, Alpes laser.
Yes. Well, there are several applications in this nutrition project. One application is relative to the measurement of a number of metabolites in the respiration, in the breath, in order to sort of correlate that with the status, the well-being status of the patient. And then we have two other liquid application where we measure certain proteins in the milk of lactating mother on the one hand, and also measure some metabolites in the urine also of babies and lactating mothers.
Thank you so much. So
And
I
how do
think
you
that
collect samples, Antoine? You simply
Yes.
take samples of the milk and then measuring in cuvette, or what else?
I'm not sure. I would say yes. I mean, the system it is based on is a Quantared system, and it's using a micro cuvette. So I guess you pump the milk into the micro cuvette and then discard it.
Because we can simply touch, with a fiber optic directly to the breast of mom and measure, milk composition during the feeding.
Yeah, you sure you want to do that?
You should ask mom.
I guess.
No, okay, it's possible. Questions that in general, milk stream product from company FOSS is measurement of composition of milk every 17 seconds in pipe. So that's why if we are going really to change life from a sampling of something and measuring in laboratory, we should think about, let's say, fiber optic probes, which will be simply attached to any pipe reactor. We really put more than 5 years in detection of tumor margin when we simply touch tissue, because a surgeon doesn't know where is the border, and they always make mistakes, more than 50%. So that's why biomarkers in mid-infrared helps to distinguish malignant cells from normal cells. So there are a lot of areas where we can collaborate, and but I really prefer to do it in line, in vivo, and not just to get samples, and measure something in vitro.
Sure. Oh, there are certainly very interesting applications using fibers to decouple the system from the measurement area.
Let's do it. Let's do it together.
Yeah.
I like it. I like this approach. Let's do together, and especially for food and beverage, so, and water for our health and our earth. So Slava, the floor is yours. Really.
Okay.
Try to summarize also. I know that you like a lot this topic, what we can do for the environmental and for our planet.
Do you see my screen?
Yes, it's not in presentation mode.
Okay, no problem. 1 second.
Yes, sure.
Is it now?
Not yet. No.
Blah, blah, blah. Wait. I have 4 screens.
Near to the minus.
Uh,
Near to the minus of the Zoom slide, bottom right.
No, I know where questions that it's open at one of my 4 screens.
Yeah, exactly. Slava, 4 screens is too much.
1 of 4. Oh my God. Not 2 screens, 4 screens.
If you disconnect all of them, it goes well. That was the best way usually.
Okay, but if you can survive with this stuff, you know, I'm trying to.
Yeah, we go on.
It's okay.
It's okay.
Big pictures. So anyway, just, you know, we have already a very good discussion today, and I would like only to focus again all of you to 3 questions which we try to answer. You know, how to motivate manufacturers of components to integrate them in complete system. I should say we really see excellent example of Vigo in this direction. And I think for us, after 23 years in business, we are also decided that probably some of them we should do together. Because with Johannes, for example, we did this kind of, let's say, prototype, but it was 14 partners together, including us, and 7 million funding from Brussels. You know, we should find something which will be more simple. And here, okay, I just cited one very nice slide prepared by Boris Mizaykov in University Ulm. There are so many components in general, you know, QCL, tunable diode lasers, FTIR, what else, which must be assembled with different detectors, spectrometers. Question, which bridge to measure, to use. One bridge can be hollow waveguides, like you see in the bottom, this blue picture. It's something embedded in piece of metal. But when we measured 7 quantum cascade lasers united in one fiber optic probe with this integrated waveguide, we found very high optical losses, something like 100 times more compared to fiber optic coupling. Here, what you see, it's a fiber optic spider kind of bundle, 300 micron each, can be even 200 micron, very good coupling efficiency with each quantum cascade laser, which was developed together with Johannes' team. And then, you know, you see how this 7 QCL are united in front of one combiner objective, which simply put it in single fiber optic probe for medical diagnostics. It's osteoarthritis diagnostics in this project. So again, message what I would like to deliver to everybody, only for the cases when you have no way to access gas or liquid like a pipe, and probe goes inside the pipe and measure everything in stream. In advantage of quantum cascade lasers, they are extremely fast. So that's why you can make measurements. Even we have a request now, ethylene production, 3.5 meters per second. And they would like to measure, let's say, catalytic gases like NOx in this stream of ethylene. So that's why here it's exactly the cases when we should select specific wavelengths, put them, you know, in pipe of the customer and measure what else, you know, like Aamir probably can understand one request we have now. Manufacturers, okay, crude oil. There are thousands of wells of crude oil. The best, the dream of this business is to measure composition of the stuff coming from Earth in real time and collect signal at one display, you know, to have kind of 3-dimensional picture what's going on. You have not only oil there, you have oil, water, inhibitors, you know, sand, gases, and so on. So it's a complicated task, but it's impossible to send one guy who will collect a sample once per day and bring it to laboratory, because it can take a day. And this guy sometimes should go up a temperature plus 50 or minus 30, you know, to collect this stuff. It doesn't work. We must change our life to the online detectors. And we should not neglect other range of spectra, yes, mid-infrared is extremely important. But here, for example, we started to make a combi sensors where mid-infrared is combined with fluorescence. And then you have fusion of data with much more accurate, let's say, results. And you can even refuse from spectrometers. You can use only one source in mid-infrared and one source for fluorescence. It will be cheap sensor in result. Okay, not to make you tired and sleepy, just to mention number of applications is almost infinite, where it's impossible to bring sample when it's 250 degrees Celsius into spectrometer. You should go with a probe inside this high temperature product. Biofermentation, biofermenters, nuclear industry, whole France, you know, where this nuclear waste goes, you should control its composition. And it's extremely expensive to do it in laboratories, to take samples. It's much easier to go with a fiber and measure directly in place. So, and environment, we already mentioned, contamination of oil can be measured, should be measured, and it should be measured by sensors which are distributed in critical points. Data should fly to cloud, and from the cloud in real time back to detector. It can be biofermenters, it can be measurements at selected wavelengths, not in full spectra, for selected wavelengths for particular parameter. So that's why I believe that the future is somewhere between maybe biophotonics, like a major niche of private investors, and information technology. So if we shall develop sensors, in our case, with our participation, fiber optic sensors, but not only fiber optic, of course, then sensors should provide sensors prototypes we develop. They have individual IP addresses. I can see what's going on in Cuba, you know, when they dry sugar in the field, you know, with my iPhone, because I simply dial IP address. So that's why if we shall fuse modern information technologies and biophotonics or photonics measurements in general, we can simply grab, let's say, more than half of worldwide market with investors. So that's why it's a topic which we should discuss with Vigo investors, for example, and invite more investors, because then it should be multiple applications. It should be volume, low cost, and maybe we should use near LED with filters, which will make, let's say, solution for end user much cheaper. So that's why we are very open to be a bridge between components. We are very open to end users, and I hope after this meeting we shall have a lot of interesting, let's say, actions to do between us. So thanks for your attention.
Thanks a lot, Slava. Thanks a lot, as usual, a great overview of all your capabilities and especially open for collaboration. So that is always what we love. And thanks a lot also for all your comments in your meeting. So is there some questions for Slava directly? So Slava, if you can stop sharing, we go back into the room.
Sure.
Thank you.
I will do.
You just go up, there is a green button, you can stop sharing. So I don't see now some questions in the room, but no, Aamir, please, Aamir, go ahead.
It's first of all, thank you for a very good presentation. It's just a comment. I completely agree with what you said about the oil measurements. Saudi Aramco has come to us with their requirement, and I think that's a challenging problem. It's not an easy problem, but that's something that is the need of the industry right now. So I'm glad to hear we're on the same page for that. Thank you.
Great. Then we have Vigo from Convergent Dental. You're muted.
Hello.
Yes, now.
Yes. I was looking at your website, and then you seem to have fibers for the wavelengths between 9 and 11, 9 to 10. That's region of interest. Do you have any single mode fibers, the polycrystalline ones?
depends on wavelengths, because we for chalcogenide fibers we have single mode versions up to, let's say, 6 maybe 9 microns. For polycrystalline fibers, we did one project for European Space Agency, but and we made it. We were the first in the world who did it, but it's too expensive. Yield is terrible because we have high scattering losses, and the stuff for the satellites were only 20 centimeter lengths. So that's why I could not recommend it even when it's our baby. But for chalcogenide, no problem. It can be plus with Verre Fluoré. They have okay, shorter wavelengths, but they have single mode fibers as well.
Very good, thanks a lot. Then it's time for Niklas. Please, Niklas. Invisible Light Labs, yes.
Also, thanks for me for this interesting talk. I just wanted to also comment on that and maybe give some example that we, for instance, have also one prototype for the detection itself, just for infrared light. But on the other hand, we are working on a spectroscopy solution. And I don't want to go too deep into how our technique works, but the idea is that we have our detection scheme also being available like a filter, in a way that, for instance, you can directly sample environmental analytes in the way of aerosols compounds. And we had done some preliminary tests, and within a few minutes, we can collect enough sample that you can make a spectroscopy analysis of the particulate matter of the aerosol. So if this is also something handy, and we just try to develop this technique further, that could be interesting for collaboration. So I'm also happy if there's some need for that, and we can discuss about it.
Yeah, I think if we shall together find end users, we really produce, for example, for pharma applications,
yes,
some fiber optic probes, cables, specially used with filter ring. It just rotating ring, relatively low cost source of light and detector. And then, okay, optics to put in fiber and out of the fiber. But this is one of the cheapest version where we can collaborate with you, with Vortex, because there are, of course, a lot of solutions where you don't need a very narrow, let's say, light source, where it can be not only LED, it can be simply broadband infrared source and filters. Yes, can be. But we should look for applications. This is a key. Who wants it?
I agree.
Thanks a lot. So I have also a question in this direction of who wants it. And apparently Mathieu from YouTube, from INO, actually says there is a need in industrial application for beyond 12 and even 15 microns. So this was originally a question for the fiber side of the technology. So mostly for Samuel, but also of course for Slava. Is there a comment? I read that.
No problem.
Slava, no problem.
Up to 16 microns.
At
Yeah.
16, okay.
Easy.
So 16, it's an easy one. I read it in
No,
your slide.
If it will be longer than 16, then we can really look for hollow waveguide solutions. But they can go even up to terahertz, you know. But for mid-infrared polycrystalline fibers are good, you know, up to 16, 17 microns.
Perfect. Thank you. And Samuel, do you have a comment on this, on the far MidIR terahertz direction?
No, just to say that we should work in a scientific purpose on hollow waveguides or Kagome design made of fluoride glass fibers. And why not made of other kind of glasses inside a collaboration?
Sounds very good plan. So I guess the YouTube is happy today, and it's time to give the floor back to Antonio. Thank you, guys.
Yes, thank you so much. So we are a little behind the scheduled time, but the discussion was really interesting and intense. I tried to summarize my impression, my feeling, but probably I missed something. Please tell me. I share the screen and I show you the summary slide. This one. Okay, so this afternoon we learned a lot of things. And first of all, I have to thank Professor Aamir from King Abdullah University that really put on the table so many questions. So I had to copy his slide, really. I copied straight his slide. I remember this sentence: sense everything, everywhere, all the time. And also practical challenge: put a benzene sensor on a drone. Then there are really, we went into more specific discussion. For example, benzene and other aromatic components in the 12-15 range. For these are necessary tunable laser, where the tunability ranges depend on the specific application. Vigo sensor raised the problem also how to go to integration for peaks sensing. So here, the strategy is really to go for hybrid integration of different components in the peaks. And on the other hand, it's also important to listen the end users and also to understand which are the driving factor of the end users, because this is the success of a business model. This coming back to sensor, we also discussed how complex is to manage a germanium foundry or foundries for waveguides. But here, really, volumes is a key factor. We have to raise the volume. So it's not only a matter of application, but also is necessary to raise the mass volume, to reach the mass volume. Fiber coupling, fibers are everywhere. Fibers are definitely the glue of this. We need to put together sensor, detectors, laser, and other optical source all together in a system as easier as possible. And okay, I took this from a comment in the chat. It's also important to understand which are the volume drivers. For example, automotive and consumer electronics, we have a white industry. And then we go to the personal health and the healthcare. And this should be integrated with smartphones and IoTs. Also, we have to take care that when we go into the medical field and life science, regulatory topics could slow down the process, but it's only a slowdown, it's not a big issue. And then I copy-pasted also the last slide of Slava, our photonics. Here is not a technical, but here there is the money, there is the view that there is a potential, a huge potential for this technology and for this market. So what I can add, we have to work together. It was a great discussion today. We learned that there is, it was done a lot, and now there is still a lot of things to do together. So now is ending the official part of the meeting. I would like to thank all the participants and all the panelists. And who has still some time to remain, we close the official part, we close the streaming, but all who like to keep here to final greetings and comments are welcome. So thank you so much to all the participants, and thank you so much for the great discussion.
Thank you also from my side. Thank you.
Thank you.